Bismillahirrahmanirrahim. Dear students, today we are going to start the 10th lecture of secondary chemistry, and we have already started chapter 16. So in this chapter, we will discuss another important class of the hydrocarbon, which is the alkynes. So we will discuss first the nomenclature of the alkane, then their preparations method, and at the end detailed discussion about the physical as well as the chemical properties. So first move to the nomenclature. So according to IUPAC system, we will select the longest chain of carbon atoms containing the triple bond. So this is the same rule just like the alkene, that we will select that longest chain of the carbon atom containing the double bond. So over here we will select that longest chain containing the triple bond. So we can see that in this case we have the 5 carbon chain, but it does not contain the triple bond. But over here we can see that is a 4 carbon chain and it contains triple bond in between them. So this is our longest chain because it contains the carbon-carbon triple bond. And we know that for the alkane we use the word ANE, but in case of alkyne we will replace the word ANE into YNE. So the second important rule, that is the numbering, and we will number from that side where triple bond is nearest. So there are two cases. So if I consider this case, and if I number from the left side carbon 1, carbon 2, carbon 3 and carbon 4, so the triple bond is in between 3 and 4 carbon. But if I number from the right side, so that triple bond is between carbon 1 and carbon 2. So this numbering is correct because we are numbering from that side where triple bond is nearest, and we know that out of these two we will use the slowest number. So this is one alkyne. So in simple word, this is called as the one alkyne. So if there is some cases when there is a competition between double bond and triple bond, so there is a possibility that organic compound contain both double bond and the triple bond. So we will prefer from that side where functional group is nearest, either double, either triple. But when there is a competition between double bond and triple bond, so we will prefer from that side where double bond is nearest. For example, this is the one case. If we number from the left side carbon 1 and carbon 2, so double bond is in between carbon 1 and 2. If I number from the right side, the triple bond is between 1 and 2. So there is a competition. So we will number from that side where double bond is nearest. So numbering will be from the 1, 2, 3, 4 and 5. It means this is the parent, this is the 1 pentene. And we will use the word ine for this triple bond. 4 ine means triple bond is in between 4 and 5 carbon. So double bond get the preference over triple bond. So then when there is more triple bonds, for example, any organic compound contains 2 triple bonds, so we will use the diene. If it contains the 3 triple bond, we will use the term triene. For example, in this molecule we have 2 triple bonds, so we can number from the either side 1, 2, 3 and 4. It means this is 1, 3 butadiene. And alkyl groups, they are giving the same naming just like the alkanes. So after nomenclature, move to the stability. So alkynes, they are more stable as compared to the alkene due to presence of extra pi bond. We know that in the alkyne we have 1 sigma bond and 2 pi bonds, and in alkene there is 1 sigma bond and 1 pi bond. So the extra pi bond make it more stable. That's why alkynes are less reactive than alkene. And we have some thermodynamic data that shows that alkynes are less reactive than the alkenes. The structure of the alkyne. So there is a carbon-carbon triple bond. So each carbon in the alkyne, that is sp hybridized. And these two sp hybrid orbitals on one side overlap with the hydrogen, on other side with the sp orbital of the neighbor carbon atom. So each carbon atom contains 2 unhybridized p orbitals which overlap with each other in a parallel fashion, and they make the 2 pi bonds. So the cloud of pi electron is present cylindrically symmetrical about the carbon-carbon sigma bond because PY and PY they overlap, PZ and PZ they overlap. So it means they are making electron cloud surrounding this sigma bond, which make it more stable. Physical properties, we know that the alkanes, alkynes, hydrocarbons, they are non-polar. And when they're non-polar, so they will dissolve in non-polar solvents, and they're not going to soluble in water. One thing. And second, we know that they are weak intermolecular forces. And their intermolecular forces increases by increasing the number of atoms. And that is called as London dispersion forces. So with increasing the electronic cloud, these intermolecular forces increases and they changes from gas to liquid and liquid to solid. And similarly, their melting point and boiling point also increases by increasing the carbon atom. For example, if I read over here, in general, alkynes are non-polar and are insoluble in water, but soluble in non-polar organic solvents. They are colorless, odorless, except acetylene, which has a garlic-like odor. Melting points, boiling points, and densities increases gradually with increase in the molecular mass. First three members, carbon alkyne, mean carbon 2 to carbon 4 are gases. Next 8 members, carbon 5 to carbon 12 are liquids, and higher members are solids at room temperature. And the reason is same. By increasing the electronic cloud, their intermolecular forces increases, which increases the melting point, boiling point, and they change the nature from gas to liquid and liquid to solid. Then we move to the preparation methods of the alkynes. There are various methods for the preparation of the alkynes. One, elimination reaction, and secondly, alkylation of sodium acetylide. But in this book, only elimination reactions are given. Elimination means removal, and the very well-known reaction for this formation of alkyne, that the elimination of hydrogen halide. That is also called as dehydrohalogenation, means removal of hydrogen and halogens. So that can be removed from the dihalide. So if we have the dihalide, it can be converted into the alkyne by the removal of hydrogen and halogen. Such kind of dihalide that is called as vicinal dihalide. So if we have the vicinal dihalide, means halogens which are attached at the adjacent carbons. And we use a base just like alcoholic KOH. It will remove first, it will remove the Br from one carbon and H from the second carbon. So removal of HBr, we get the double bond over here. So in the next step, again this base will react and it will remove the HBr. So Br from the alpha carbon and hydrogen from the beta carbon, and we get the triple bond. It means vicinal dihalide converted into alkyne by the two step. In first step, removal of HBr, we convert into double bonded molecule. And then again removal of HBr and we goes to the triple bonded molecule, which is the alkyne. So there is some possibility that if we use the alcoholic KOH, the terminal alkyne may rearrange to make the internal alkyne. So prevent from the rearrangement, we use sodium amide in liquid ammonia and we get the terminal alkyne. Terminal alkyne means the triple bond at carbon number 1 and 2, between carbon 1 and 2. So for example, this is the vicinal dihalide. We use sodium amide. So in two steps, one HBr, second HBr, we get the triple bond, and this is CNH. First, this is called sodium alkylide, means this form the salt, and then it reacts with the water to make the alkyne. So this is the terminal alkyne. So we use sodium amide to prevent its rearrangement, and we get the terminal alkyne. Secondly, these alkynes can also be prepared from geminal dihalide. Geminal dihalide means halogens are attached with the same carbon atom, and we use the base sodium amide in liquid ammonia. So similar to the previous, one removal of HBr, we get the double bond, and then again removal of HBr, we get the triple bond. So in this book, only dehydrohalogenation is given, and this dehydrohalogenation from vicinal dihalide as well as geminal dihalide. Reactions. So before going to the reactions, we discussed its reactivity, and we said that these alkynes, they are unsaturated. They has the triple bond. It means that is unsaturated, so addition can take place. So the most reaction, they are the addition reaction. So triple bond can be changed to double bond, and the double bond changed to the single bond. And number second, this bond, carbon hydrogen bond, is polar because of sp hybridization of this carbon. So this hydrogen can be ionized. It means this bond can break and some substitution reaction can take place. So alkyne undergo addition reaction as well as substitution reaction due to easy cleavage of carbon hydrogen bond. So first, going to the reactions, we discuss this cleavage of carbon hydrogen bond. So this carbon hydrogen bond is polar. So by the using the base, it will abstract this proton and we get this alkynide ions. This is called alkynide ions, which can be produced. So now this negative ion, it can attack on any other electrophile, and we can get some substituted proton. So that's why we said that this, by removal of this hydrogen, it can undergo some substitution reactions. So for example, we would add sodium amide, so it will remove this hydrogen and we can get this sodium alkynide. Similarly, this is the ethyne, so it has two acidic hydrogen. So sodium, we add the sodium and we get the disodium acetylides. So these hydrogens which attach to the terminal alkyne or the hydrogen attached to sp hybridized carbon atom, this hydrogen is acidic, and this is called as acidic nature of the alkynes. So this acidic hydrogen is very important to differentiate between terminal alkyne and internal alkyne, and for that purpose we use some test. For example, in the first test we add ammonical silver nitrate solution. So by adding ammonical silver nitrate solution, these two hydrogens are replaced with the silver. So it forms disilver acetylide, which are the white precipitates. Similarly, we can also add ammonical cuprous chloride, and these hydrogen, which are the acidic, can be replaced with the copper, that is called dicopper acetylide. So this disilver acetylide, they are the white precipitates, and these are the reddish brown. So formation of these colors shows that the alkyne, they have the acidic hydrogen, and the acidic hydrogen can be only obtained from the terminal alkyne. And interestingly, these precipitates, these disilver acetylide or the dicopper acetylide, can be converted back to the original alkynes by the addition of acid of that. By that solution, by the addition of acidic solution into that, we can make those alkyne again. So these alkynides are used for the preparation, purification, separation, and identification of the alkynes. So these tests are very important for the acidic nature of the alkynes. Now move to the addition reaction of the alkyne, just like similar to the alkene. So in alkene, they converted to alkane, but now for the alkyne, first they will change to the double bond, mean alkene, and then the double bond will change to the single bond. So first reaction is hydrogenation, mean addition of hydrogen. In the presence of catalyst, we use the nickel, generally we can use over here. So first we add the hydrogen, so triple bond change to the double bond. Then again hydrogen added into double bond and it converted into the single bond. So this is called as reduction, and this is called as full reduction, mean alkyne is changed to the alkane. So this is called as full hydrogenation or full reduction. But in some cases we can stop this reaction of addition of hydrogen at alkene stage. So if we stop the reaction of alkyne at the alkene stage, that is called as partial reduction or partial hydrogenation, and it can take place by using some catalyst and after poison, means stopping the reaction at alkene stage. And for that purpose we can use various reagents, and there are two possibilities, that when we will convert alkyne into the alkene, then there are two possibilities, either we will get the cis alkene, either we get the trans alkene. So if we add the hydrogen in the presence of this catalyst that is called a Linrol catalyst. So it will convert the alkyne into the cis alkene. So both hydrogen will added from the same time. So this is stereospecific, mean one alkyne will convert the only cis. So there will be no transport, 100% this cis alkene. But if we add sodium in liquid ammonia, we get the trans alkene, 100% trans alkene. So alkyne can be converted to cis alkene or trans alkene depending on the reagent which we use for this partial hydrogenation. So we must learn about that because some question can be given that how can you convert alkyne into cis or trans alkenes. Then hydrohalogenation mean addition of hydrogen as well as halogen. So addition of hydrogen and halogen, we get the dihaloalkane, and the addition takes place according to Markovnikov's rule. So in the first step, this is the ethyne. We have the HBr. So hydrogen goes to one carbon, Br goes to second carbon, and triple bond change to the double bond. So first, this is the intermediate that is called as the vinyl bromide. And we know this double bond will change to the single bond. So there is another molecule of HBr which will add into this vinyl bromide. Now we can use the rule Markovnikov's rule because this reagent HBr is unsymmetrical. This alkene is also unsymmetrical. So according to Markovnikov's rule, negative part of the reagent will go to that carbon which has less number of hydrogens. So the Br will go to this carbon and hydrogen will go to this carbon. So CH2 will change to CH3. Single bond CH and Br mean 1,1 dibromoethane. So the addition of HBr in the second step takes place according to Markovnikov's rule. Hydration. So addition of water, that is called as hydration. So this addition of water takes place in the presence of mercuric sulfate in sulfuric acid at 75 degrees centigrade. So similar to the HBr, now we have the HOH. So hydrogen goes to one carbon, OH goes to second carbon, and the triple bond moves to the double bond. This is called as vinyl alcohol. But before adding another water molecule, this vinyl alcohol undergoes some rearrangement. And the hydrogen of this alcohol, it moves from here and it goes to this carbon. And there's a make a carbon oxygen double bond, and this double bond moves to the single bond. And we get the CH3, single bond, C double bond, O and H. So this is acetaldehyde. So this vinyl alcohol during the reaction undergoes some rearrangement and hydrogens move from one atom to the other atom. This is called as tautomerism, as we discussed the keto-enol tautomerism. So if we have the propyne, another, so this is the propyne CH3, C and C triple bond CH, then addition of water. Now the addition of water takes place according to Markovnikov's rule, and the OH will go to that carbon which has less number of hydrogen. So OH will go to this carbon and H will go to this carbon. So the triple bond change to the double bond. Now again this molecule undergo the rearrangement and the hydrogen is shifted from oxygen to carbon and the double bond change to the single bond and we get the ketone. This is the acetone. So we can say this is our result that the addition of water to the ethyne we get the aldehyde. But addition of water to the higher alkyne, every time we will get the ketone. Next, bromination mean halogenation. So addition of halogen, that is called halogenation, and we get the tetrahaloalkane because first if we use the bromination, so first bromine molecule, one bromine goes to one carbon and second bromine goes to second carbon. So triple bond moves to the double bond. So again in the next step, addition of another Br2 molecule and this double bond will move to the single bond. So this is the bromine, addition of bromine into the alkyne, this double bond and then again bromine molecule. So double bond moves to the single bond because these bromines are the symmetrical. So there is no problem for the Markovnikov's rule and we get the tetrabromoethane. So this is the bromination as well as the chlorination. The last reaction, that is the ozonolysis. So for the alkene, we know that the reaction of alkene with the ozone, we get the carbonyl compounds. Same is the case, the reaction of alkyne with the ozone, this carbon-carbon triple bond breaks and we get the acids, carboxylic acid. So we get two molecules of the carboxylic acid. So previous for the alkene, we get the aldehyde or ketone, but in case of alkyne, we get the carboxylic acid. So if we make the summary of our lecture, we discuss about the nomenclature, preparations, physical and chemical properties of the alkynes. And if we have any question, you can ask me in the comment box and we can discuss. Thanks.